Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, it's 5 past, so I think we might as well make a start. It gives me great pleasure to welcome back Christian, who interned with us several years ago in the old building, and we had a great productive internship back then. So Christian is now nearing the end of his PhD at Ulm University. He's in the mobile HCI group, and today he's going to talk to us about his work in projected user interfaces. Thank you.
Hey, thank you very much, Steve, for the very kind introduction, and good morning to you all. Thank you for joining my talk this morning. And I'll be talking about supporting the mobile nomadic user through projected user interfaces. Now, if you hear projected user interfaces, you probably think of a lot of works that even have been done by Microsoft, which, for instance, target creating smart spaces, smart environments in rooms, creating entertaining rooms and interactive rooms where each display is transformed into an interactive experience. And these use fixed projectors in the room. Then there are also a lot of works on handheld projection and mobile projection, where the mobile projector is steered. And this is used for different application domains, like the medical domain. It's used for gaming and information spaces. And there's also a lot of research going on increasing the accuracy and maturity of tracking technologies, like with OmniTouch. However, was only little work so far that targets not only projected user interfaces, but really tries to address mobile nomadic usage scenarios. So people on the go doing their everyday activities that they normally do with mobile phones and other mobile devices. And my work, my research wanted to investigate this more, how we can support users in this regard. So let's start by thinking together about what are the current deficiencies of mobile interaction with mobile phones and mobile tablets. And because it's already still quite early in the morning, I thought I'd start with something entertaining. And I love this video because it shows very well the benefits that a large display would have in our everyday life for all sorts of applications. And there's a lot of research, of course, going on foldable, bendable, and flexible displays that tries to address this. But so far, we're not there yet. So far, there is this rivalry between the physical size of the display, which is coupled to the physical form factor of the mobile device. And if we had such a device, despite providing good call reception and signal quality, the device would lose its mobility and also lose its eligibility of being a mobile device. So one of the first deficiencies of current mobile interaction is the limited display space. Another deficiency is that these devices are carried in pockets and handbags, so they cannot optimally support the awareness of the user, alert the user to new information despite simple vibration alerts and things like that. They can also not really support the user during continuous interaction because they have to be operated in hand and stowed and get out again. The research on wearable gadgets is trying to address this as well, but it's a deficiency of current mobile standard devices. Another deficiency is that collaboration isn't really well supported on these mobile devices. So if users wanted to share content, they cannot show it to multiple people at the same time. They may even have to hand out the device containing all their personal belongings and have to hand out control over their very personal device. And this directly relates to a fourth deficiency, which is that privacy isn't well supported, especially during collaboration and sharing on these mobile devices. there are many research directions that trying to address these, ranging from simple vibration alerts over audio interfaces, smart gadgets like smart eyewear, smart watches, and of course all the sorts of pervasive displays and research going on in that domain. But one possible solution that I researched addressing these deficiencies is personal mobile projection, because these projectors, they have become so small, so tiny that they can easily be integrated into smartphones. There are projectors, so-called projector phones out there. They can be integrated in tablets and in accessory devices. And the vision that manufacturers basically sell is this one, that you can just instantly project information on a nearby wall. Unfortunately, this is quite the only vision that manufacturers have with these devices. So this is a picture by Microvision, and it comes natural that this is the one of the few visions, because this is how projection was always used in previous times. So like here, right now it's not very feasible to build these large displays as a physical display, so we use projection. Or we use projection where we don't have a larger display available so that we can bring the projector there. However, there are a lot of different mobile scenarios that projectors can support, and as I said, I looked at how mobile projectors can support these nomadic usage scenarios. And for these scenarios, there are mainly two problems. There are some application scenarios where this remote steering and interaction is very valuable. For instance, this is work by Willis et al. Called Side by Side, where people steer a character and they do very simple interactions like boxing the other party. But as we found out in a previous work, or in initial work on projection in mobile usage scenarios, is that this remote interaction and this remote steering, be it behind the device, be it on the touchpad, this bimanual control is really hard for users to maintain. And also this indirect interaction using a cursor is much slower than what people achieve and how they perform when interacting through direct touch on mobile phones, for instance. And we tested these applications like gaming, browsing, maps, and also drawing to research very accurate tasks. And really, these remote interaction control really didn't work well for users. And there's another reason why this remote interaction for this mobile everyday scenarios may not be very suitable, and that is that these projectors, they currently have a very low brightness. So compared to the 20,000 lumens of the sun, these 50 lumens, and that's already quite much for an inbuilt projector, is really not enough to create these projections, these large projections in uncontrolled environments, in arbitrary use cases that users face throughout their day. And you need to shut the blinds to really use them. However, if we go with the projector closer to the projection surface, we lose size. We lose what is always marketed as something very valuable of projections. But still, we retain a display of about 8-inch size, which is very flexible, which is a second display, another display that can be used for interaction, and which already today can be used in uncontrolled environments, not in direct sunlight, but just in a normal room, as you will see in the future projects. So the core idea of my research and of the projects that I'm going to show is this idea of mobile projection within reach. So literally that the projection can be grasped, can be touched, and that the projection is very close around the device or around the user to address the deficiencies of mobile interaction. And there are all sorts of research questions, of course, that arose around this one, like in and output modalities, where to position the display, where to position the projector, what are suitable applications, and how to increase the awareness of the user. So in the following couple of minutes, I'm going to show you these 4 projects which employ this idea of mobile projection within reach. And later in the talk, I will kind of broaden the scope and discuss this in a broader scenario, including other wearables and other possibilities to address these deficiencies. So in the first project, the pen book, this was part of an EU project called Hospital Engineering. And in interviews and focus groups with nurses and doctors, we found out that there's still a lot of paper-based workflows going on in the hospital. Despite all software that is available and all advantages that digital information provides, the flexibility and the expressiveness of freehand input and of paper and the mobility of paper is still cherished a lot in the hospital domain, and therefore it is used a lot. And so our idea was to think about how we can address that, not to create the perfect software, just the next version of software, but create a device that would combine touch interaction on a digital device with handwritten input on real paper. So we came up with this idea to integrate the projector at the top of the tablet and to project on real paper on the inside lid of the cover of the tablet to allow for writing with light and with a real paper haptic experience. And that's how this looks like. So we have this touch interaction on the tablet. You can also interact with the rear side of the pen. And then it allows for very precise writing with light. And we have this toolbar available across all applications, which allows for changing pen color, tip size, background of the paper, and so on. And of course, it allows for scrolling horizontally and vertically, so that you have like a virtually endless paper space. And then for the hospital domain, we developed some applications, like here, correcting things in application forms or getting context-aware help on very complicated surgery forms. So this is the patient side. And for the doctor side, this is one example where basic selections are performed on the upper touch screen, and very precise handwritten input to organic schemes can happen on the paper. And because at that time there was no good support on mobile operating systems for external screens, we used another phone inside this closure that drives the projected output. We have a semi-automatic calibration procedure to calibrate between the pen that uses a noto paper and camera technology, and we reverse engineered the protocol of the pen, and together in this automatic calibration we then receive a very precise input on the paper. And this was studied in a small user study with 10 students who annotated websites with shopping items, doing their personal notes on the paper, and just by clicking they came back to the shopping item, so it allowed for easily comparing several items. And they really liked the overall design, but what was interesting was that it really depended also on their liking of their own handwriting. So there were some that really liked handwriting for all its advantages, and some of the students, they didn't like handwriting anymore, and especially not their own handwriting, so they didn't like that. Yeah.
I was curious, one of the obvious drawbacks of that are the shadows that showed up in some. Did you get much feedback on that?
The shadow, because the projection comes from like the other side, the device, the shadow is really most of the time. I mean, it's in the best scenario, it is exactly under, like under the hand. In the worst scenario, coming from this side, it goes in this direction. But at least during writing, it isn't really a problem.
So I'm just curious what the users thought.
Yeah. No user complained about shadow problems, exactly. And right now, this is also studied in a larger user study in a model hospital with real nurses and doctors, and this in Duisburg in the Fraunhofer Institute, and this study is still ongoing. Yeah.
So that you've got a screen there, and then you're writing on this surface. But one of the interesting things about writing is that you write at a different angle to what you're viewing is. Is there anything about that form factor which makes it more difficult to write, or I mean, with people twisting these things, would you want them separable in some ways?
Yeah, because this lid, I think this is a very good quality of projection, because the lid we created first a 3D prototype and then had that built as a real aluminum case, and we had a really, really small, thin lid and the paper on top of it, so there wasn't really a difference in the size that people could just like put their arms on top of it. And regarding this rotation, I think that only depends on the viewing angle of the tablet device, and that was with this one okay. So I think this didn't impose any constraints on that. Yeah.
I thought it was very clever how you mediated the issue about technology, large screen, a mobile phone behind, and a horizontal surface. Just wondering whether you also had an opportunity to test scenarios where you could just remove the large screen and just have a mobile phone, because I can imagine you can just attach the projection on the mobile phone.
Yeah, that would be exactly the next project. Thanks for yeah. So this is the Surface phone then, where we wanted to use the same idea, so attach a projector to a mobile phone and to similarly increase the interaction space for the mobile Nomadic user. And in this project, we also wanted to go one step further, which to not only support one user, but multiple users. Because on mobile phones, the collaboration support is still very bad. There are many proprietary sharing techniques within the mobile operating systems that are okay for just sharing content, but the collaboration support isn't really there. This is due to the small display size and also just due to a lack of software support. And the place where this mobile or this collaboration on content is at the moment supported the best, I think, are these multi-touch tabletop experience, where users just drag around content, share content, work collaboratively on content. So yeah, my idea was how would it be possible to create this ad hoc mobile tabletop experience, yeah, on the go and in an ad hoc fashion to support all these kinds of collaborating and sharing experiences. Yeah, so I created first a mock-up prototype, which we see here, which is the mobile phone, creating a projected display right behind it. And here we use in this mock-up prototype, use a Microsoft Surface, which tracks the phones with bytecode tags to create this virtual projection behind it. But yeah, in a minute, we'll also be presenting a real device that I built. And with this one, we wanted just to extract users' likings, test different applications, different setups and transfer techniques. So regarding the setups, this type of device, of course, can be used as a single-user device. So one idea is that you have your active browsing tab on the projection and the other browsing tabs or the task manager on the mobile phone, or when playing a game, that you have the game view on the projection and the controls on the mobile phone, in order that you don't occlude the game view with your fingers. Then, of course, there's the scenario where you have one device but multiple users, and there you can really leverage the public-private support of this setup. So the user owning the device can decide which images or which content he or she wants to share through the projection, and the other user in turn has the opportunity to explore this content, to do these pinch operations, work with the content, do annotations and things like that. And then finally, there are these multi-device, multi-user scenarios, where there's also different types, depending on the setup, different types of intimacy that can be supported. For instance, in the top scenario, and this is quite an opponent-like setup, where users have their private display on the phone, and also there's a notion of a private projected space where the other party can't reach as easy as I can reach my projected space in front of me. And the opposite at the bottom, where both users give up their private spaces on the phone, and they have also similar access to the complete projection. And of course, this would extend to 3 or 4 users, although not all setups of intimacy could be supported then. And during the study, we really saw users change their positions according to the task. So if they wanted to solve the puzzle, half of the participants would change from an opponent-like setup to this very intimate setup to collaboratively solve the puzzle and look at each other the pieces that they had on the phone. Other results of this first study, another result of this first study was that users really liked this multi-user and multi-device setups, but didn't really didn't find the single-user setup that useful. So they imagined they wouldn't buy such a device only for the benefits of the single-user applications. We also investigated transfer techniques. So participants used something like a proxy technique that mediated objects across the border. Then a touch swipe technique, for instance, in the Scrabble game, the letters were placed on the bank and then just transferred with one touch swipe on the Scrabble board. And finally, a technique called human link, which is a little inspired by the Lightspace project by Andy Wilson, where the human body acts as a link between both displays. And participants found this very natural and intuitive, but it performed the worst because, as we also see in the video, as soon as participants touched the phone, the projection, which is coupled to the device, moved as well. So items never really ended up where users wanted them to be. On the other hand, the proxy technique was perceived as very slow because each item had to be transferred individually. So overall, they preferred the touch swipe technique, which is also versatile enough to also be applicable to pictures and all other sorts of content, that you first bin all the items on your phone and then transfer them in one row. As I said, after this, I also wanted to build this device, and I created this 3D enclosure, which allows for, in this case, an iPhone to slide into the case. It's self-contained and self-powered, and it contains a Pico-P engine that I took from a Microvision commercial device. And going through, sitting at the bottom of the device, and then going through this mirror at the top, which can also slide into the device and get out again when the device is placed on the table. It allows for a projected display behind the device that is about the size of 8-inch. So it's almost twice the size of the 4-inch of the iPhone 5. And the next challenge was how to track the user's interaction, how to track especially the touch position and the touch event. And because in this project I didn't want to use any additional hardware, despite the fact that at that time mobile very small depth cameras weren't commercially available, I really wanted to just use standard phone hardware that a normal phone could just slide into this enclosure and just work. So that's why this device uses the camera to track the position of the finger. And of course there's a calibration set up beforehand where we measure intrinsic, extrinsic parameters of camera and projector and compute a homography between those to come up with this view on the bottom left on the bottom left picture on the bottom left picture in this slide to find the position where the finger of the user is, and then to detect the touch event. We use the vibration that the user induces to the table upon the touch that travels through the table to the accelerometer of the phone. And there's also an automatic calibration, very brief automatic calibration procedure. As soon as the device is placed on the table, the device will vibrate 2 times and measure the vibration that goes out to the table. And by that, we can adjust the thresholds a little. So, of course, it still won't work on granite. So, despite the calibration, the table needs some freedom to vibrate. But, yeah, we can adjust the thresholds and to distinguish between a hard touch and a light touch. And we wanted at least this multimodality, because on these multi-touch tables, there are at least these two very important interactions, that you touch something and that you start dragging something, either by touching longer or by using multi-touch. Because we don't have multi-touch in this scenario, and we cannot touch longer because of this kind of tracking through vibration. Therefore, the idea to have at least a hard and a light touch. Here we see in a video how the finger is tracked, and we had another user study where participants touched at circles with a light or hard touch of different sizes and at different positions. And they also performed some gestures. And the results of this are that for a first prototype, the accuracy wasn't too bad, but there's still a lot of room for improvement, especially with smaller sized circles, and also the different touch intensities didn't work too well. So on average, only in 70% of times participants touched with the right intensity, and especially performing a strong touch was harder than we thought. But there are solutions to that. The first solution regarding the position of the finger, for instance, when we looked at where participants exactly touched the surface, it's evident that it was really easy for participants when they had a very good view on the upper left. They had a very good view where exactly the finger would touch the target and touch the table, whereas on the bottom right, the finger occluded this position. And we know that from mobile phones that there then occurs this overshooting or undershooting of targets. And here with the projection, we see a similar trend, although on mobile phones it's that you undershoot on the upper left and that you overshoot on the upper right, and here it is that you just overshoot on the bottom right. So by computing an offset function, we can at least correct for this overshooting we get an improvement of around 4% on average, and especially for small circles, we can improve that by 7.5%. And then regarding the touch intensity, participants told us that if they had a visual feedback of their last touch, of the strength of the last touch, it would be more easy for them to maintain a mental model of the hardness of their touch, and there should also be some function for personal adaptation of these thresholds. And the gesture accuracy with 86% was quite okay. So we learned with the Surface Phone, we learned about the applications and different setups and transfer techniques that participants desired. And this is also available as an open source toolkit, including the 3D enclosure and all the code under this URL. And with this project, we not only address display space, the deficiency of display space on mobile devices, but also collaboration and privacy support. In the third project, which is the interactive phone call, we wanted to take this idea from the co-located setup that we had before to a remote located setup. So we all probably have experienced the situation where we're in a call, we don't have a headset available, or we don't want to, we don't bother getting one out and attaching it. So we're on the phone call, we are in this closed and quite intimate setup of a phone call with the other party, but all content on a phone is quite locked because the phone is at our ear and we can't really easily access that. So the idea in this project is that we equip the phone with a projector at the bottom, and during the call, the phone can project, again, multi-touch or at least a touch tabletop surface on the table or on a nearby wall, so that the user can explore his or her own content and also collaborate and share content with the other party during the call. And after several paper prototypes and focus groups with users, we came up with this setup where we use a desktop-like metaphor, so application icons and application windows, which can then easily be shared or copied respectively by dragging it over this flexible bar in the middle that also allows to resize the spaces in favor of each other. And here we see a user using the device first to explore his own images, and then he starts an interactive session. So there's a handshake beforehand, interactive session with the other calling party, and uses the device to share pictures. We see the color coding shows ownership, and there's also means for adjusting privacy settings depending on the items. And this can be used for sharing pictures, for conducting whole presentations in the shared space, or as seen here, for stacking multiple calendars over each other and then easily find free spots. And with this project, we also wanted to investigate this privacy aspect more. So we built another version that was just for the mobile phone and using speaker mode, where the only difference is that users could only see one of the two spaces at one time, and they would use a swipe gesture to switch between those two displays. And finally, a third alternative where there is no notion of a private and a shared space, but just a simple screen sharing of the whole screen, but which also allowed for non-verbal communication using these pointers. And the outcome of this study was that participants didn't like the screen sharing approach because although we had these icons that would always show who was peeking at which display. They didn't really know what the other user was doing. They didn't know about the content. They didn't feel comfortable with this approach. They felt a lot more comfortable with the idea of this private and shared space, for instance, on the mobile device. However, the privacy support, as they said, could only be really leveraged on the projected display, because only the projected display provided the required size and to see the private and the shared space at the same time to really get this awareness of what the other user is doing and how he or she is working on the collaborative content. So with these three projects that are more like in the one way or the other, they want to achieve other types of input and sometimes a tabletop experience and increase the privacy of the user by using multiple displays. And these are already, they could be built today. They are already quite real devices as such. With the fourth project, this is more like thinking 15 years in the future, where I thought about getting rid of the display of the mobile device altogether and follow the basic idea of pervasive displays, which so far hasn't really come true. The vision of pervasive displays is that they are all around us every time, or all the time, and so far this is not the case. Maybe this won't be the case in the near future, I don't know. So the idea here was that each user carries their own pervasive display on the floor using projection. And the ideas that in this regard are, of course, what are the applications that are suitable for such a constantly available display on the floor? What is a good visualization? We were quite sure that people didn't want to walk, do their shopping stroll with their Windows desktop background picture on the floor in front of them all the time. So we knew we needed a good visualization for that. And of course, this is similar to questions that the HoloLens project by Microsoft must be asking themselves. Because, and the videos that I know, they are targeting specialized domains like playing at home or exploring the Mars. Whereas, I want to draw your attention to the fact that here I'm looking at these everyday mobile scenarios, being on the go, facing arbitrary situations and also using arbitrary content. So it's not the specialized domain. So we really need an information space concept and design that can handle a lot of different application types. And just to think about possible application types, these include, of course, notifications, reminders of all sorts, personalized advertisements, navigation that I just have to follow a projected path to my destination, and also that that the system maintains my awareness of people around, of friends nearby, and so on. And one solution or a first decision was to use really the complete world as your virtual world, as your virtual display, and to use this projected rectangle as a window into your personal virtual world. Because a big advantage that this brings is that it allows for an implicit interaction and for a peripheral interaction with the content. So that I can just, while on the go, I can see something at that position, a picture that was taken at that position on the floor. If I want to hide it, again, if I don't want to disclose it to people nearby, I just do a step to the side. If I've seen something too late at a last glance, I can just turn around and see the content there. Simple another simple example is that I could just record my footsteps walking through my virtual world, and when I get back to the same spot again, I see my footsteps from the last instance that I was there. And to have an arbitrary and or an visualization concept that works for arbitrary use cases, we created these three types, or we created three different types of visualization. So the first we called word graffiti, which is just digital signage on the floor, which could be there for real. Then this navigation visualization, and finally, interactive content. So by using flat 2D visualizations for all that is non-interactive, the user quickly sees and is aware of the content that is meant to be interacted with. And so we have many different application types. For instance, there's the note type that you can put a note on your threshold at home to not forget to buy milk when you cross the threshold the next time. So when you leave the house, you can literally stumble over this box and find this reminder. Another example for static content are pictures that are taken at that place and which, for the same user or even for another user using the same device, can be explored at that specific position later in time. And then there are these other types of interactive content where you want to interact with the environment. So for instance, you could call an elevator early up front before reaching it. When we place these boxes in all hallways leading to the elevator, you can already, while approaching the elevator, quickly take up this box and call the elevator in the direction you want. Then there's this third type of content which doesn't have a real location in your virtual world, but where we will roll this dynamic information like a new message along your way for some seconds, and then it will stop at that position, and during that time the user will either have noticed it and maybe interacted with the box, or if not, the box is ignored and a little later in time removed at that position, and then we place it again in the user's path later in time. So this type of information only has a temporal fixed location for a certain time, and then we put it again in the user's path later in time. This is for the representations of boxes, and then we have the representation of spheres for content that is of immediate urgency, like an incoming phone call, where as long as the call is ringing, the sphere accompanies you, and you can either take the call or dismiss it. And I call this type of visualization dynamic causally located augmented reality, and I think it would be also very relevant for other projects like Microsoft HoloLens or Google Glass, etc. If they wanted to address and think about these scenarios on the go where you have to interact with arbitrary content, arbitrary types of apps, and not in a specialized domain. And in fact, I'm just about doing that myself. I've built this prototype combining Oculus Rift with really very wide view cameras, so there are multiple lenses in front of the original camera to allow for sensing also the space on the floor. And finally, you would also want to interact with the content. You will see that shortly in the videos, so I only go briefly over that. You can select content by steering a cursor below the content, take it to the hand. As soon as it's in the hand, it can show more private content in the hand. You can have previews, decisions, selections. You can deselect and snooze it, or remove it by throwing it over your shoulder. And of course, there are means of transferring content, exploring content in detail on your phone, or sharing content to the mobile world. So here we see me interacting with a dynamic information while on the go, picking it up to the hand and exploring it. Here we see this digital signage on the floor, which, as all other content, is really at a very fixed location in my virtual world. And this is an example of picking up a box and reading the content. And there are also animations that provide these, visualize these transitions of content from floor to hand. And there's also a change of focus of the projector depending on the depth of interaction. Here we see another user taking a picture with the mobile phone and then sharing this to the specific location in front of him. Here we see me finding a note in front of a colleague's office to meet him at the coffee place. And two further examples are this navigation, which can also or should also include turn-by-turn navigation signs to allow for taking shortcuts, that you're not too bound to following this projected path. But on the other hand, it allows for peripheral interaction. You just have to follow the path using quick lenses. And finally here, this personalized advertisement where I find a personalized offer in front of a shop and I can have a preview in my hand. And I implemented this by bringing together a lot of different components, a depth camera like a Kinect camera, a projector, and then a servo controller to change the focus of the projector, and an inertial measurement unit. And the system is still quite bulky, mainly due to the fact that it has to run on a laptop PC and not on an embedded platform. The user's fingers and gestures are tracked by the depth camera, and the depth information is also used to adjust the focus of the projector to allow this range of interaction. And we also detect steps by combining inertial measurement, accelerometer, and optical flow information of the depth camera. And with that, we can detect 90% of the forward and backward steps accurately. Of course, in a real deployment, it would require to combine this with GPS outside and Kalman filtering or other indoor localization techniques. But for proof of concept exploration, this was already worked well enough to explore the interactions. And we're also working on a smaller version of this, which is currently under review, where you are wearing it on the hand. It would also allow this projection on the floor and projection in the other hand for exploring content on the go. So, for a first summary, by bringing the projection closer to the surface, we lose this large space that is always marketed by manufacturers of projectors, but we still retain the affordances, the flexibility of another second display that can be used for multi-modal interaction, such as in the pen book, for creating ad hoc merge displays. So they all employed this idea of mobile projection within reach. And we see several very unique affordances of projection. So these ad hoc merge displays, they couldn't as well be supported right now using smart eyewear, for instance, or this peripheral interaction on the floor, because the field of view of smart eyewear is currently very limited. This projection on the floor really allows for this peripheral display that I can see in my visual periphery. And as such, this mobile projection within reach is really able to address several of these mobile deficiencies of current mobile devices. and as that, it allows to support the mobile nomadic user through projected interfaces. And in the future, I now want to broaden the scope to I'm interested in broadening the scope to the whole wearable design space, such as in the past I've looked at how mobile projection can address the deficiencies of mobile devices. I'm now interested in how all these new types of wearable devices are able to address the deficiencies of each other. So how smart rings can address the small input space of smart watches, for instance. And as one example of that, let me briefly show you Glass Unlock, which I will present at the upcoming Kai conference, which takes the deficiency of mobile devices that they are susceptible to shoulder surfing and smudge attacks during unlocking, and addressing it with the very private nature and private display of smart glasses. So as we see here, the user wearing the glasses sees the randomized pin pad, but other shoulder surfers or secretly watching cameras, even multiple cameras, cannot make any sense of the input on the phone. And in a user study, we found out that first, the time only, input time only increases by the factor 2, which is not too much considering the increased security that this technique is proof against and secure against shoulder surfing, smudge attacks, and video and camera attacks, which are often difficult to tackle. And also interesting was that participants preferred the slowest input technique because that was the technique that avoided display switching the gaze between the mobile, the near eye display of the smart glasses and the mobile device display. So they favored the technique that was the slowest one. So to sum up, in this future design space of supporting the mobile nomadic user, I think I've shown that mobile projection has very unique values, and I think it will pertain these values of being able to create ad hoc collaboration without prior network setup, of creating these device-centric and unique types of augmentation, for instance, on paper, and using this, allowing for this paper haptic feeling. And it requires the least augmentation because it can be integrated in the existing mobile devices of the user. It doesn't require to wear additional devices like the others do. Of course, on the other hand, other wearable devices in the future will provide a better visibility than mobile projection, and in some cases, maybe more socially acceptable. So, but they all can address the deficiencies of each other in mobile interaction. And with that, let me very much thank you for listening to my talk, and I'm very happy to take further questions. Thank you.
So we're getting close to the top of the hour, but do we have a question? Any further questions for Christian?
Yeah.
James.
James was a little bit quicker. Yeah.
So, do you see personal projectors coming out in phones? I mean, what's the sort of roadmap for that? Is it a long way off? Are there technical barriers in the way, or is it really a social acceptance barrier?
Yeah, I would have to be a manufacturer probably to answer that. I mean, there is, for instance, a Samsung Galaxy Beam phone which uses this touchpad metaphor to interact on the content, and it's. I think they really try to have a good usability with that, and it's not really bad, but it's really the use case in everyday scenarios is really limited. I think there's this new one from this tablet from Lenovo, which projects to the side a second projection, which enforces me to sit on the right side of the round table, for instance, in order that I have the surface at that place. So I think there are many decisions that manufacturers would have to think over, allowing more flexibility, allowing many really using the affordances of this second mobile projection. So far, as I said in the talk, it's really all based on this prior usage of mobile projectors, which was just to project something remotely away and maybe interact with that. So I don't think there are any technical barriers. If I could have built it, Samsung and Lenovo will probably be able to do that as well. It's socially acceptable, I think, for the project that I've shown, despite the last one, the ambient mobile display. Of course, this is going into the same social acceptability discussions like smart eyewear is facing. But the other ideas of supporting tabletop interaction, I don't think there are issues of social acceptability that are hindering that.
Kenton.
Half-formed question, but I was really interested in the earlier the mobile phone projection with the mirror and things relative to the
Surface phone.
Yeah.
Mm-hmm.
So where you've got the mirror that projects down onto.
Yeah. Mm-hmm.
And one of the things I liked about that, I think more so than some of the pervasive concepts that you talk about, is that I think it sort of distinguishes between display as something that you're looking at versus display as an action. And in particular, when you think about this in the context of collaborative scenarios where you're treating those technical possibilities as ways of achieving a particular act in a social context. And maybe we can talk about this later during the interview, but have you got any sort of comments on display as an act, social act, versus display as something which is just information coming into your eyes?
So having it here on the table versus wearing smart glasses, for instance? Or
no, more how we think about the notion of display as being something. So in a collaborative context, I might be deliberately showing you something, and so the interesting thing about the form factors that you showed with that Surface phone was that it's allowing me to go from an individual device to a collaborative scenario, and that's what I felt was interesting about it.
So the act of switching it on does two things. It gives you more screen real estate, but it also makes a statement, right? Because you're now projecting your content, you're sharing that in a...
Yeah. And so it feels like that you can think of that is thinking about display not just as the input or the information coming into your eyes, but as this social act. And that's why I kind of thought it was potentially a richer way of thinking about this than maybe some of the other pervasive things. And if you think of the later pervasive concepts in terms of display as an act, might that allow you to reformulate some of the applications of that you have?
Yeah. So for instance, in this MD context, you could easily transport all these ideas of the Surface phone to the MD concept, so that two people walk up and they have their pervasive displays on the floor and they merge it and share content in that space, which again with smart glasses, of course, that would be possible, but it would allow a lot of tracking. So thinking of doing that in the wild, it would require tracking the other user, tracking the other display, knowing about all display sizes and configurations. Maybe these are different manufacturers, different models people are wearing. With projection, this one is really, really easy because both users just instantly see what they are projecting. They instantly see their display and they can do the calibration themselves. They can just manually merge multiple displays and create this shared space with that. Yeah.
Okay. I think we should stop there. So let's thank the speaker one more time. Thank you.